Welcome to Chapter 5, Harnessing the Secrets of the Nucleus. Our story today starts not in 1945, but actually 3 years earlier, in a small squash court underneath the football stadium of Stagg Field in the University of Chicago, in Chicago, Illinois. A small Italian immigrant by the name of Enrico Fermi is putting together the first atomic pile, doing a quick experiment to try to see whether he can create the first controlled chain reaction. He had previously won the Nobel Prize in 1938 for learning how to slow down neutrons and to aid the capture. Fast neutrons end up bouncing off the nucleus and don't get captured, but slow neutrons, as we talked about last chapter, can be absorbed more easily and more readily. But of course, as Italy and Europe became under the control of fascism, he escaped to America where he became an American citizen. And so he found himself in the University of Chicago. So he's putting together a 20-foot high by 20 feet, 24-foot based pile containing uranium and uranium oxide blocks intermixed with graphite as a moderator. That graphite is there to help slow the neutrons. Any neutrons flung out by a reaction would then pass through the graphite, slowing down before they strike the next uranium block. Now he has cadmium pushed into there at certain points so as to prevent too many neutrons flinging out. That the cadmium is the control rod, essentially the neutron absorbing component. So once he started in December 2nd, 1942, he starts his trial run where they slowly remove each of the cadmium rods one by one. Gets to the last cadmium rod. As they slowly pull it out, the detector starts to pick up some radiation. They start to hear chatter, and it begins to chatter more and more as they pull the rod further and further out of the block. Of course, they were had lots of precautions in place where there is people ready to put the rods back into place. There was a assistant with an axe ready to cut a rope to swing cadmium rods instantly back into place if need be. The last precaution they had, like students with cadmium solutions going to have to douse it if it looked like it was going to be a runaway reaction. Would that have worked? Well, thankfully, no one had to find out. So he slowly removed the last cadmium rod almost all the way out and saw a continuing constant stream of radiation that was picked up by the detector. He let this reaction go for 4.5 minutes before starting to replace the cadmium rods and slow reaction back off and stop it. Now, while it didn't produce it much energy, it was barely enough energy to run a flashlight, but it was the first controlled reaction. This was the proof of concept we needed before we could build a reactor. This was the first proof of concept before we could even build a bomb. We needed something to prove that we could control the nucleus and make this go on in a very controlled fashion. Now, the basic nuclear reactor has a couple key components. It has your rods of some sort, usually uranium oxide ore. Now, they don't have to be incredibly high purity of uranium 235. You only need like maybe 3%, 4%. not like the 90% you need for a bomb. You're going to have some sort of uh, moderator that's going to slow down the neutrons, and you're going to have some sort of control rods that will be put in to stop to stop the reaction. Now you're also going to need some sort of coolant because to take the heat away. That is one of the key factors. You need some coolant that's going to run this out. And of course, you need some sort of vessel that has both thermal shielding to keep the heat from melting the whole vessel and biological shielding so we don't kill all the scientists running this. This is a basic image of the nuclear reactor. Now, here's the generalized process. Here we have our fuel in here that's surrounded by the coolant in the primary loop. We have uranium oxide clad with steel or zirconium alloy to keep it in shape. Our moderator in this case is water. So we're having this is going to be all contaminated water, going to be heavy water in this loop. All this water is going to be channeling through, pumped through at a constant rate, and going to be allowed to boil some water in a adjusting non-contaminated line. So the heat will be transferred from this hot loop under very high pressure where it cannot boil to a lower pressure, easier to boil system. So as the water boils, it turns to steam and can then go through and push and turn this turbine generator, thus generating our power. And of course, as that steam passes through a third cooling loop, it can then be cooled and condensed back to water where it can be pumped through and boiled again. So the coolant outlet temperature here is 550 degrees Fahrenheit, above boiling. So it needs 2,000 pounds of PSI, pounds per square inch pressure to keep that there. As long as the coolant is flowing and we keep this at high pressure, everything works fine. Now, the reason why most of the nuclear power plants, you see those large, unusual shapes, those large, like, scoop shapes, is because those are that tertiary cooling line that they use. They air cool that water as they move that around that entire giant, like, hollow cylinder. That's using to cool the water in the tertiary line. Now the control rods are often either boron or cadmium because of their capabilities of absorbing neutrons. Now, this is not the cleanest method. In fact, fusion would be far cleaner as it produces less byproducts and less radioactive waste. However, you use much higher temperatures. And right now, we have no known material that can contain such high temperatures. The closest thing we have is a tokamak reactor, which would have to use magnetism to contain the fusion reaction. But that's still many years away if we can even manage that. The first reactor would come 9 years later than that first atomic pile in Stagg Stadium in 1951. It was a promise of clean, cheap energy. But this promise has given way to fear, and we've lost a lot of the reactors. In 1975, there was maybe 56 plants. 92 maybe got up to 109. But by 2021, there's maybe about 55 plants with 94 active reactors between them that they've been either shut down or decommissioned, or they've had problems, and basically we're not really building them as much anymore or at all. Now, there's several major dangers that we have to worry about, whether real or true. We have the actual danger of the plant itself. We have limitations on the fuel source and the hazards associated with disposal, and the cost of nuclear power in general. We will look at each of these in turn. Now, whether there's a chance of an actual nuclear fireball, that is not really possible. The nuclear fireball, like a nuclear explosion, would require high concentrations of U-235, and the fuel source just isn't that much. Just as I said, 3 to 4% concentration. So very low concentration, very low chance of explosion, at least from nuclear source. Now, can there be other explosions? Yes, very much so. All due to, well, there's various reasons due to failure. So there are still dangers, but not quite as bad. These reactors are designed for a slow release. Now, there's still, we can have non-nuclear fires and explosions which lead to that come from core overheats. Our first example is in December 1952. We had a partial meltdown in the Idaho plant near Ottawa, Canada, where 4 control rods were accidentally removed, causing a partial meltdown, which basically means the rods actually start, the fuel source actually starts to melt and lose its shape, which then adds problems where it's harder to put the rods back into the designed holes if the fuel sources aren't contained. This caused the destruction of the reactor and the building and the contamination of approximately 1 million gallons of water. One of the next problems was in 1957, a fire in the Seascale plant off the Irish Sea ended up releasing radiation into the English countryside that we believe caused the death of about 39 people due to the radiation. Now, there's been many small and minor disasters since then, but I'm going to talk about 3 more. One of the biggest ones on U.S. soil, it'd be in March 28, 1979, best known as 3 Mile Island, near Harrisburg, Pennsylvania. There was an equipment failure that led to the disaster, but it was also, in addition to human error. There's a common thing of a lot of times human error leads to this, whether something screws up and then people start panicking, and panic leads to further disaster. But this caused the loss of coolant. Basically, the coolant that was supposed to be cooling the reactor and keeping everything going got boiled off. And once that boils off, things start to heat up, and that's where you get the meltdowns. The core ended up heating up to 2,000 degrees Celsius, which led to the partial meltdown. Now, this then flooded the containment building with large quantity of radioactive water, and we ended up having a small radiation leak to the atmosphere. Now, as I said, that's not too bad. Yes, there's radiation escaping, but it was mostly contained within the building itself. The really bad one was April 16th, 1986, Chernobyl, Ukraine, down here. This started with a faulty reactor design from the first bit. I mean, it was Soviet Russia, so I mean, take that what you will, and then a series of human errors added on top of this, including a simple failure to follow the safety protocol. If you don't follow the designed way to prevent further disaster, it just spirals out of control, which is some of the fear. This caused an overheating and a rupture to the pile. We had at least 2 explosions that ripped away part of the core and blew off the roof. This may have been caused by the catalysis of splitting water. That the coolant in there got so hot that we split it down to hydrogen and oxygen, which, as we know, hydrogen, very flammable. When you have those high heats of uranium, and a highly flammable gas, we have an explosion. So two explosions blows us up and sprays large amounts of radioactive smoke and debris into the atmosphere. Because of spraying it so high into the atmosphere, it got caught with the wind currents and spread far and wide. First being detected in Finland and Sweden, which is how we knew about this disaster. The Soviet Union probably would have tried to cover this up if not for the fact that everyone else kind of got a little bit of the backlash from this. It's spread into Europe and Asia and even some into the Western Hemisphere. So, but the most part, it can largely contained in the Ukraine. There's 2 dead in the plant, 29 dead later from radiation poisoning, and the fallout led to at least initially 135,000 evacuees. Though from 1986 to 2000, there's been maybe 350,000 evacuees had to move out of their homes because of the danger zone. This was found in the radiation was found in tree bark up to 40 miles away. And even now, there is 1,000 square mile zone that it's just too radioactive for long-term residents. Now, even after the case, there's still some lingering effects from the fallout, that it's getting into the food supply, it's getting into the water, and it's causing problems, especially, say, in the thyroid. It causing thyroid abnormalities. As we'll see with over like 150,000 cases of this. Now, iodine is taken up by the thyroid, and we'll talk about this more later. There is a particular type of iodine, iodine 131, that is a byproduct of this radiation. This iodine can get into milk. So when people drink milk, it get uptaken in the thyroid and cause radiation damage. In Gomel, a town near Chernobyl, before the disaster, there was maybe 1 to 2 cases of thyroid cancer a year. But 5 years after, there was at least 38 cases of this. So far, there's been estimated somewhere between 17,000 and 475,000 deaths because of this incident, just from radiation damage. The exact amount, not quite known, because it's kind of hard to say how much of this cancer was brought about by this. And the other one, which has probably happened in many of your lifetimes, it happened in March 16th, 2011. It was Fukushima in Okuma, Japan. So around that time, we had a big earthquake on the 11th, which part of the fail-safe of the power plant is that when something like that happens, you have automatically shut down the reactors. You stop it going. Unfortunately, with most of these reactors, they don't have a instant shut-off valve. They don't have a stop reaction right now. It's more of a cool down period, that as you put in the control rods, it slowly peters out. With that in mind, there were some electrical grid problems that necessitated the running of the emergency diesel generators to keep the coolant flowing. So as the reactors are petering out, they're still producing heat. So you still need that coolant to help cool them off, slow this process down. Well, that earthquake, because it happened off the coast of Japan, also caused a tsunami. And so that tsunami with 46-foot waves then flooded the plant and caused a shutdown of the generators. Now, since they shut down the generators, the coolant stopped flowing and the coolant boiled off, and we have meltdowns in 3 out of the 4 reactors, and hydrogen explosions in 3 out of the 4 reactors, as we can see here. This caused the release of contamination between the 12th and the 15th of March, and with radiation being released in the atmosphere, they had to have a 20-kilometer evacuation zone with somewhere near 154,000 people needing to be evacuated. There was ended up being a large amount of radioactive water being released into the Pacific Ocean. Something like 18,000 teraberkels worth of cesium-137 during the accident, and much more after it, for years afterwards. Now, to get a fill, 18,000 teraberkels. Hopefully remember Berkel from last chapter. Well, a kiloberkel would be 1,000. A mega would be 1,000,000. A giga would be 1,000,000,000. And a tera would be something like 1,000,000,000,000. So that's 18,000 trillion berkels worth of cesium-137 being released. So a large amount. And so we still have problems with that to this day. I think they've had to build a seawall to help prevent further leakage. As we can see, the fears of the danger of the nuclear power plant is not entirely unwarranted. Well, it's all about safety, really. But one of the things to note is that newer plants would hopefully have more safety features. As you improve technology, as the science becomes better well known, the technology can further become advanced and improved. The first car you build, incredibly unsafe. That 100th car you build, probably 1,000 times safer. Remember, we didn't have seat belts initially in cars till people figured out, oh, people keep being flung from the vehicle when they crash. We didn't have airbags in cars. Oh, people are bashing their brains in on the dashboards. So the more technology is used, the safer it can become. If we don't build any new nuclear power plants, we only use the old ones we got without real improvement. We're only using older, more decrepit, more dangerous technology.
Despite all the gloom and doom, nuclear power is actually relatively safe. If you consider Fukushima, which was like incredibly poorly designed, like putting an outlet with a live wire in the splash zone in SeaWorld, where it was, as soon as a tidal wave, it was bound to fail. How many people died from Fukushima? Maybe 14. There was a lot of evacuees, but very few people actually died from the disaster in itself. More people, on average, die from a coal fire plant per terawatt hour. There is far more fatalities from coal plants than there are from nuclear power plants. It's just that when disasters happen at nuclear power plants, it's bigger. It's like the airplane effect, airplanes don't crash very often, but when they do, it's such a big thing that the news pays attention. If you paid attention to all the cars that crash, it'd be a lot more dangerous and a lot scarier.
The other issue is supply. If we're just looking at uranium-235, uranium-235 is only 0.72% abundant of all uranium products, which means we only have maybe a 50 to 100-year supply of the stuff that we can get out at a reasonable cost. So it's not going to last us too long just on that by itself. However, there is other possibilities, one of which being a breeder reactor. The breeder reactor is just a nuclear reactor that produces more fissionable fuel than it consumes. And the basic idea here is that we make plutonium, which is another very easily fissionable material. We bombard uranium-238, the 99.9% abundant material, or essentially 99% abundant material. We bombard it with a neutron. It becomes U-239, which then undergoes beta decay to form Neptunium proton, a Neptunian cation. Now that Neptunium cation can then absorb an electron from somewhere to become Neptunium neutral, and then undergoes another beta decay to form plutonium cation, which then can absorb another electron from somewhere to form plutonium neutral. So that plutonium then can undergo a reaction. We can use that plutonium as our fissile material. And if we do this, we have just by looking at that alone, we would have enough material to last us thousands of years. In fact, these guys run under a different design. They actually use liquid sodium as a coolant. So this is often called a liquid sodium fast breeder reactor. But essentially, we're using, say, molten sodium to transfer heat from one place to another. And it still runs basically on that steam line in the end. It's just we're transferring the first initial heat from the sodium. Of course, that also means sodium is going to be a lot harder to boil than water. So we don't have to worry about the heat being nearly as high. We can get the sodium a lot higher heat without issues. Unfortunately, there is certain technical and political reasons why we can't really use these, at least not very commonly. One of the main reasons is being any one country that has one of these, you become a target for terrorism or proliferation of nuclear weapons.
The plutonium formed by these breeder reactors is the same type of plutonium that can be easily used, well, not right easily, but easily used to make a nuclear warhead. Unlike the U-235, which is in low abundance and have to be purified out of large amounts of U-238, plutonium formed in this method is already purified. So the plutonium could be used as reactor fuel, or it could be used as a bomb, that implosion-style detonation bomb that we talked about last chapter.
So any terrorist who wants to try to steal your plutonium going to attack that factory. I mean, you don't want Iran to have this because we don't want Iran to have the nuke. So it's often not very politically safe to go this route. And plus, plutonium is far more dangerous to the human body. Just inhaling just a small amount could cause death. And the fact that I think Russia has used plutonium pellets to assassinate many people is related to that fact. And then another reason why we're so worried about nuclear is because the waste, the byproduct, the disposal of these byproducts, many of which are still radioactive. We have to get rid of them. They're not useful anymore, but we have to figure out a way to get rid of them. So these guys have to undergo multiple decay chains to get to a stable isotope. And then we don't have to worry about them anymore. Now, with that in mind, much reactivity will disappear eventually, but not all, and it will take a very long period of time for that to happen. Which is why when we deal with radioactivity, we often discuss half-life, which is literally the time it takes for exactly 1/2 of any given quantity of an isotope to decay. Each element has its own specific half-life. That iodine 131 takes 8 days to decay to half its quantity. So that means if I have 100 grams, 8 days later, that's 50 grams. But another 8 days later, so 16 days total, it's down to 25 grams. 8 days later, so now it's up to 24 days, almost a whole month, it's down to 12 and a half grams. 32 days.
After 32 days, iodine is down to 6.25 grams, and this will continue like this every 8 days. Each isotope has its own individual half-life. C14 has a half-life of 5,730 years.
235, which would be 700 million years. Krypton 93, 1.3 seconds. We have plutonium 239, 24,000 years. U-238, 4.5 billion years. Cesium 137, brought up because that's what got dumped into the Pacific Ocean, 30 years. Of course, cesium, all that cesium will have a limited effect because it's where it was dumped into the Pacific Ocean. It could be largely diluted as it spread worldwide. So, yay, it's not going to necessarily harm much marine life because everything gets a small dose rather than some things get a huge dose. But one of the key things to remind us is in order for something to be considered safe, it has to undergo 10 half-lives. So it means essentially by 10 half-lives, we have about 0.1% of the original material left. So iodine 131, 10 half-lives would be 80 days. But for uranium 235, that'd be 7 billion years. So depending on what you're dealing with, you have a wholly different problem. There is no known way to change the half-life. We can't increase the temperature. We can't increase the pressure. We can't use magnetism. All we know how to do is to safely store this away. And even then it's so. We have to store this long term. Waste products for these guys include things like medical diagnostics and therapeutics, like syringes and films and all sorts of material like that, with gloves, clothing, and instruments that have been dosed with this. Used fuel, and of course, uranium and plutonium from decommissioned bombs. All this has to be stored. Now, we can store some of this and we can store this in two different types of forms, two different classifications. We have low-level radioactive material and high-level. The low-level, right now, we just can kind of bury it underground in certain federally approved sites, and that it's not going to really cause much damage to the environment. But the high-level one is kind of like the uranium and the plutonium. We need to store it for thousands upon thousands of years, well beyond our lifetime. So we have to worry about that. We need a sealed and remote and dry location for like tens of thousands of years. Well, originally there was plans to put it in the Yucca Mountain in Nevada, which the idea being there, if you can keep this dry, it can be stored in these steel containers, corrosion-resistant containers, for hopefully forever. But if there's any moisture, even though they may be corrosion resistant, heat, because these things will still produce heat as they're releasing the radioactivity. there's produce heat plus water going to lead to corrosion, and if it corrodes, it can leak. If it leaks, it can get into the groundwater and thus contaminate large amounts of groundwater and make people sick. So we need someplace really dry. Now, Yucca Mountain, I don't think is currently in use. I mean, it was being optioned, but I think Obama took it off the table. But before we blame, thanks, Obama, Trump was looking into it, and then he decided not to go with that. And right now, Biden is also not going with that plan. So we've had 3 generations of presidents all kind of saying, yeah, we're not going to go with that. So right now, what we have to do is we typically store the used fuel rods for 1 to 10 years in a cooling pool. Then we store them in a steel container that we surround, a steel cask that we fill with inert gas, and then surround that by either more steel or concrete, essentially enough protection that the radiation doesn't escape through, and these can survive like being hit by a train without breaking open. I guess they're good for now. It's a short-term goal. I mean, it'll hopefully hold for several decades, if not a century or two, but we have to figure out a plan eventually. It's not a long-term plan here. And the final problem, I'm not even going to waste a slide on that, is just the cost of this. To build a new building has a really large startup cost. And once you have it built, there's a lot of maintenance that needs to go into that. Because if you don't maintain your nuclear power plant, you risk some of these issues that we talked about. And so, long story short, even though it's, I guess, less air pollution than our different sources, less air pollution than coal, coal's still 2 times cheaper. And right now, that's what we're going with. We're going with cheap. You could get coal. We have a large quantity of coal. We have the plants already built, and we don't have to worry about really disposing of it afterwards. Maybe carbon sequestration, but we'll talk about that more later. But for now, I mean, that's what we got to deal with. Maybe the nuclear power isn't the best idea, but where we can really use this is in medicine. Remember that we have alpha, we have beta, we have gamma, and they all have different degrees of penetration power, but they also have varying degrees of ionizing power. That alpha particles are bigger, slower moving, but they also do more damage. They can be stopped by your dead skin cells, by thin clothes. Beta particles can be stopped by heavier clothing. They're like a little bit faster moving, do a little bit less damage. And the gamma particles are really hard to stop, but don't do nearly as much damage. It's like consider a crowded alleyway where alpha particles are trying to drive through and beta and gamma. Alpha particles are like a big semi truck trying to drive through this crowded alleyway. It only gets part of the way down the alleyway before it gets totally trashed, but it trashes everything in the meantime. Doesn't penetrate very far, but smashes up everything it hits. You have a sedan driving through there. It gets a little bit farther, maybe dings a few things, but it does a little bit damage, but not nearly as much, but it gets further through. Now, a motorbike would be like our gamma particles. It can get all the way through. It bumps into a few things, but it doesn't do nearly as much damage as it gets all the way through. So the bigger the particles, the more damage it can do, but the less it can penetrate before it bumps into anything hard enough to stop. And it brings us to several types of damage, because we could bump into anything between water in the body to enzymes to DNA and RNA, causing all sorts of chaos. You could turn the DNA into something useless, or you could turn it into something actively harmful, which is some problems here. So we have two types of damage that can be caused: somatic damage, which is injury to a living body causing illness or death to that body. That could be organ damage. It could be like too much radiation causes a low white cell count. Could cause fatigue and nausea because it's attacking the stomach lining. Somatic damage would be like the people who undergone radiation treatment, their hair falling out. Various types of cancer can be caused of that, organ failure, all this types, and eventually death. Thus, the amount of somatic damage depends on the type of radiation, the size of the dose, and the fitness of the person being dosed by it. So, if you're healthier, maybe it's going to do a little bit less damage. But a certain large amount of dose will cause death no matter what. As we saw last chapter when we looked at Slodden and Dolphin, that they got dosed with a high amount, full on. They just knew they were already dead. They went to the hospital and then succumbed to their somatic damage. And there's genetic damage, which is damage that is transmitted to future generations. Now, this is like birth defects. And while we have observed this in the laboratory with animals, it is less common in humans. We haven't at least directly seen this as a result of in humans, but that's not to say it doesn't still occur. It just either whether we haven't seen enough of situations where this has occurred, where we've been dosed with radiation for this to happen, or we're less susceptible to it. Whatever the reason, we haven't really seen too many cases of this. Where we can really use this, it happens to be in various types of diagnosis and therapies. That we talked about the thyroid being a large uptaker of iodine earlier, that this caused a problem after Chernobyl. But using that very fact is actually can turn into something that's very helpful in the long run. That because the thyroid takes up iodine, we can on purposely dose it with small quantities of I-131 that give people small amounts of sodium iodide, of heavy sodium iodide, to drink. And when they drink it, it will give up beta and gamma rays. Now, in small amounts, we can actually see the uptake and see the particle, the rays coming off, and kind of see and get some sort of image of a blobby image of the thyroid. That being useful for saying, is the thyroid completely working like it should? If so, we should see complete uptake and spreading of the iodine throughout the whole thyroid. If there's some part of the thyroid that is not working, say cancerous or something like that, you'll be big black spots that the iodine has not been uptaken like it should expect it. So that can be very useful to say, is this organ working properly? Did it take this material that it's supposed to take properly? And in larger doses, the iodine 131 can actually damage the thyroid and kind of reduce the number of thyroid cells, thus helping repress hyperthyroidism, a disease of an overactive thyroid. By doing this, we can help bring it back down to normal levels. Now, another one another one actually uses technetium, 99 technetium, a metastable compound. That when we make this metastable compound, it will just undergo a gamma decay to become a stable version of technetium. Now we can put this technetium into compounds and then embed them into organs and thus produce gamma rays in the desired place. It's useful for imaging, as this only has a half-life of 6 hours. Technetium was our first artificial element in this way. It was discovered in 1937 in UC Berkeley by bombarding molybdenum with deuterium. Now, technetium comes from the Greek word technetos, which means synthetic or artificial. So it was a hard element to find. Now, another thing we can do is, as we know, radiation therapy. Cancer cells will divide much more rapidly than normal cells, and so they are more susceptible to the ionizing radiation. And so if we use radiation beams of various types, we can damage them and stop their growth a lot easier. Of course, that's why the same growth is why hair follicles and stomach linings often be affected nearly as much. Now, there's a new technique out. Well, it's not really new, but that involves focused gamma beams from cobalt 60, where they run this cobalt 60 beam in a circle around the body, where it's focused on one spot in the body where the tumor is in the center. So as they encircle the body, so they're going around the body, the beam is passing through, and it's all converging on one spot. As it converges on this one spot, the tumor's getting the large dose while the outer parts are getting a much smaller dose. And so we can focus on the tumor and kill it. And one of the last techniques is positron emission tomography, or PET. PET is a technique that produces images of planes within an organ, generated through the analysis of gamma rays that are emitted by collisions of positrons and electrons. So, and a positron is formed when an element has far more protons than neutrons. And when a proton will decay through positron emission, it forms a neutron to make things stable again. Quick reminder, when a positron hits an electron, they form two gamma rays that head off in opposite directions. Now, this can be used with carbon 11, nitrogen 13, oxygen 15, or fluorine 18. We put these guys into compounds and that will be used by a given organ, and we put into the body. So what happens is when they get uptake by the organ, they're going to produce positrons, hit a nearby electron, shoot the gamma rays on both sides, and you're inside this ring, much like an MRI, and it's going to detect the gamma particles hit on both sides, and there's going to be a bunch of these being formed, and so you can get these thousands of little slices of the organ, looked at it from both sides, and thus get a three-dimensional image of what's going on in that organ. And we can actually see how this molecule is traveling through the organ. The tomography comes from the Greek word tomos, which means slice or section. But so this shows the molecular traffic. This is probably most often used in the brain or in the heart, where we actually need to see how it's being used. One of the most interesting ways is in the brain, because they put this in things like fluorine 18, which they attach to glucose. Well, glucose is the only energy molecule that is used by the brain. So it's the sole source of energy in the brain. So when we put this into glucose and uptake in the body, we can see this go directly to the brain, and we can see how the brain works when it's thinking, when it's listening, when it's watching. When you give it certain drugs, how are they being utilized by the brain? Because they're going to flow to what part of the brain is being utilized at this given time. Suddenly the frontal cortex is needed to do this. Oh, the cerebellum is being used for this. The hippocampus is being used for that. So you're going to see the flow of this molecule as the brain is being utilized. And so we can help see and understand the brain in this way. Also, it can help diagnose abnormalities and that, oh, it's not going to this point. Maybe there's some problem with the brain. Maybe we need to treat that. And one of the major advantages of these is they also have very short half lives. 2 minutes for oxygen 15, for example, 110 minutes for fluorine 18. So even though they do a little bit of tiny damage, it doesn't do it for very long. Very small doses. Very small doses. Now, because uranium and all these other nuclear molecules have a set half life, we can learn some really interesting things about them. As they have a set half life, we can actually determine the age of certain objects. That U-238, because it has a half life of like what I think we said like 4.5 billion years, and it decays through multiple different steps to lead 206. Lead 206 not being the most common isotope of lead. We can assume all lead 206 comes from U-238. And in this way, by looking at the ratio of uranium 238 within the molecule and lead 206 within the molecule, we can actually determine how old this rock is. If you have a meteorite hits the Earth with uranium and lead 206, we can figure out when was this meteorite formed. In fact, this is how we determine the surface of the Earth, that the Earth is somewhere between 3.5 and 4 billion years old by looking at the ratio of lead 206 to lead to uranium 238. The idea is like even though U-238 undergoes multiple decays in this chain, the first decay, which is uranium 238 undergoing alpha decay, is the slowest step. It's the one that takes the longest to form. In this case, it is called the rate determining step. Now, rate determining step is the slowest step in a sequence of steps that by itself alone determine the rate of the entire multi-step process. So it'd be like if you're trying to fly to Chattanooga, and so the first step you have to do is drive to Nashville. Say you drive to Nashville, that takes you about 2.5 hours, and then between the time you got on the plane and flew to Nashville, it took 30 minutes. That first initial drive, I know that's amazing. Imagine having like airport security being that fast that you can get on the plane and right off. But that the whole thing is that driving to Nashville was the slow step. That slow step that controlled how fast it took to get there. Now, say instead of that 2.5 hours, once we got there, we were stuck in airport security for 5 hours, and then there's delays on the tarmac, so it takes a total of 6 hours between when we got to Nashville and when we flew to Chattanooga. In that case, the initial 2.5 hours looked like nothing compared to all that. So it all depends on what the rate determining step is. So if we look at that rate determining step, we can find out something to do with that. Now, that's where carbon dating comes in. Carbon-14 happens when naturally occurring nitrogen gets bombarded by neutrons to form a carbon-14 molecule and a proton. Well, this carbon-14 can get incorporated into CO2. That CO2 can then be absorbed into plants. And any plant can then either die and be used into various things like fibers or building materials like wood or It could be eaten by animals, and it'd be absorbed into animals. And then animals are going to eat other animals, and this essentially everybody has a low level of carbon 14 present in them at any given time. Now, carbon 14 will naturally decay back into nitrogen 14 through beta decay, but the half life is 5,730 years. So essentially, it remains constant. It remains constant in all people until the point of death, at which point, when carbon decays, it is not being replaced. And so, by looking at the ratio of carbon 14 in the atmosphere versus carbon 14 in the body versus ratio of carbon 12s and 13s, we can look and see how long ago something had died. How long has something died? With that in mind, I'll bring you the example of the Shroud of Turin. It's a famous biblical artifact, was believed to be the burial cloth of Jesus Christ, that after he was crucified on the cross, he was wrapped in a shroud, burial shroud, and put in the tomb. And this was presented as Jesus's shroud. And you see, like, oh, appears to be a human features embedded in the cloth. Well, the story comes from 1988. The shroud first appeared in France in 1350, 1360 AD. For this to be true, that shroud would have to be over 2,000 years old. Obviously, sometime, I don't know, 30 AD, something like that. Hard to say. But so they tested the shroud. They tested the shroud with carbon dating. They found that it was only somewhere that the fabric that was in the shroud ranged only somewhere between 1260 AD and 1390 AD, meaning there it could not possibly be Jesus's shroud. That is because, well, that would mean the fabric would have had to been dyed almost 1,000 years after Jesus. So this was clearly a fabricated biblical artifact. Now, what does that say about Christianity? Nothing. It just says this particular artifact, not real deal. Carbon dating can be used for lots of different things. Now, of course, the older things are, the harder it is to get an exact date on how old it is, which is why they can't narrow it down to a date between 1260 and 1390, but they do have an approximate idea. They said in the article it couldn't be older than 1200 AD. So there's no way it could have been the situation. Finish up by talking about how do we actually detect this radiation? It's odorless and colorless and still very much so dangerous. So how do we deal with this? And that's where we get things like Geiger counters. The basic idea of a Geiger counter is that we have a little tube filled with inert gas and two different types, a central wire and brass joint, and a window that prevents anything from going in besides radiation. When radiation goes in, it ionizes the gas, which then can connect a circuit and thus create a current, which creates the chatter that we hear in the Geiger counter. It's named after Hans Geiger, a student of Rutherford who first invented this. There's other things like scintillation counters, which essentially uses zinc sulfide that fluoresce when hit with radiation. Essentially, we can use the fluorescence, how like it's shooting off light as it gets hit with radiation. And we can even have things like film badges, where they're like a film plate that will darken based on how much radiation it absorbs. That's an example of more of a passive method. The passive in that you have to look down and see it. It doesn't just go, hey, you're dying here. You have to look down like, oh, I've been heavily dosed. This one is go, make the loud noises, the chatter, to get the hell out of there. The film badge, just after the fact, you're going to say, oh, I need to go get some treatment. Which brings us to terms like REM. In the older books, REM isn't in there. In the newer books, REM is. But it's a Rontgen equivalent man. It's a unit of measurement of biological effect of ionizing radiation. A Rontgen was a unit of radiation. Well, this is then they factored it in with how much does the different types of radiation affect people. Like alpha particles do certain amounts of damage versus beta and gamma, so it's now factored into how much of a biological effect it would have on someone. And so even if we want to avoid all radiation, even if you say no nuclear reactors in my backyard, we're always being hit with radiation. In fact, we have constant background radiation, which is the low level of natural radiation to which we're all exposed. That even if we want to avoid, say, no x-rays for me, I don't want any radioisotopes put in my body for medical science, you're still only cutting out 18%. You're going to have radon in the atmosphere. You're going to have cosmic rays, glowing rocks, so even potassium. You eat a banana, you have a small amount of radioactivity in your body because K40, the radioactive potassium, is 0.01% of all potassium, so it's impossible to avoid. But radiation could be used for harm or for good. It all depends on how we treat it. Do we treat it with respect? Do we recognize the dangers? It's like treat it like a deadly cobra. You don't want to play around with the cobra. If you treat it wisely, you can be safe. So our last thing we will talk about is a writing prompt. A writing prompt is one of the methods of disposing of radioactive waste was to hypothetically send it up and place it on the surface of the moon. So send it up and store it on the surface of the moon. And so I want you to spend 150 words or so, put on a discussion board, essentially, do you think this is a good idea? Bad idea? Discuss what your proposed advantages and disadvantages of this method of storage of nuclear waste. Discuss on would this be a practical application? Yay or nay? Come up with your advantages and disadvantages of doing just that. I'll see you for chapter 6.